So we continue our study of the violation of the classical linear regression model, and the violation that we now deal with is called autocorrelation. Recall from our previous study of linear regression that given a population regression function that is linear in the parameters, then the Gauss-Markov theorem says that given these 6 assumptions, the OLS or the ordinary least squares estimators are blue, that is best, linear and unbiased estimators. The violation of the Gauss-Markov theorem that we are concerned with in this module is the 5th assumption, that is the error terms are uncorrelated. You would remember from elementary statistics that this implies that expectation of the cross product of error terms is equal to 0. That is, expectation of sigma I into sigma j equal to 0 for all I not equal to j. The violation of this assumption, that is the case when error terms are correlated to each other, is the problem of autocorrelation, as we will now graphically illustrate. To better understand the nature of the problem, let us first look at the correct formulation. In the xy plane, we have drawn a regression line represented by the blue line and the green dots which represent the sample points. Now note that the sample points do not all have to lie on the regression line because of the existence of an error term EI. However, under the basic assumption of regression, the error term is randomly distributed. In fact, under the classical linear regression model, the error term is normally distributed. Hence, what we see is a regression line and sample points which are randomly distributed around the regression line. This is the correct formulation. Let us first look at the case of positive autocorrelation, that is when error terms, instead of being randomly distributed, tend to be positive if the previous error term was positive and tend to be negative if the previous error term was negative. In that sense, they follow the last few error terms. Positive autocorrelation is the more common form of autocorrelation because most economic variables tend to show a lot of inertia. For example, if we take y to be the GDP growth rate and x to be time, then good GDP growth rate in this quarter is likely to be followed by decent GDP growth rate in the next quarter, unless we're talking of a crisis situation. Hence, because of this inherent inertia in most economic variables, positive autocorrelation is more commonly observed. Another type of autocorrelation is negative autocorrelation, wherein a positive error term in this period is likely to be followed by a negative error term in the next period and vice versa. This is shown on the left hand panel of this slide. To illustrate this more vividly, we have connected the error terms in the right hand diagram of this slide, and as you can see, the yellow line connecting these green points keeps crossing the regression line in the center. Note that negative autocorrelation is not very frequently observed, but if we need to take an example, we could consider excess supply on the y-axis and time on the x-axis. We see that excess supply typically follows a cyclic behavior near the equilibrium point, and hence we would typically tend to see negative autocorrelation. To put it more formally, we study only linear functional forms for the error term, that is, forms wherein the error term in this period is linearly dependent on error terms in the previous periods. More specifically, we call them autoregressive or AR schemes. For example, an AR1 scheme refers to dependence of this period's error term only on the last period's error term. For example, this equation wherein sigma t is equal to rho sigma t minus 1 plus nu t, wherein rho represents the effect of last period's error term on this period's error term and nu t represents a totally random component. Similarly, we can talk about AR2, AR3 and ARP schemes, wherein ARP scheme refers to the fact wherein sigma t is linearly dependent on p previous error terms, and in all of these we see the existence of a random component which is given by nu t. We now study the effects of autocorrelation on the blue properties of the ordinary least squares estimate. So we see that just like in heteroscedasticity, the estimates of the regression coefficients are still linear and they are still unbiased. However, they are no longer best, that is, they no longer have minimum variance. We also observe that just as in the case of heteroscedasticity, the estimate of the variance of error term sigma I square is no longer unbiased. We have estimated sigma I square by taking summation ei square by n minus k, but we now observe that this value is no longer unbiased. Hence, the estimates of variances of the regression coefficients alpha and beta are also biased, which leads to t-tests and f-tests which are now unreliable. The key difference from heteroscedasticity in this case is that we can say something more specific about the nature of the bias of estimates of sigma I square. For example, for positive autocorrelation, the estimate of sigma I square will typically have a downward bias. Hence, the standard error of sigma I square that we estimate will be lower than the true standard error, in which case the t values which will be calculated will tend to be higher, and this leads to a greater probability of a type 1 error, that is, the probability of rejecting a true null hypothesis. As far as detection of autocorrelation is concerned, we face the same problem that we do in the case of heteroscedasticity and multicollinearity. That is, since the population regression function or the PRF is not known, hence we do not know the actual error term, which is sigma I. That is, sigma I square is not directly observable. Hence we need to make a proxy for sigma I square and use ei squares as proxy for the actual sigma I squares. Hence all the tests that we talk about here are probabilistic cases, that is, they assign a certain probability that autocorrelation is present. The three tests that we will be talking about in this module in increasing order of generality are the Durbin-Watson D test, the Durbin H test, and the Breusch-Godrey test or the LM test. Now the Durbin-Watson D test makes four very restrictive assumptions. The Durbin H test relaxes one of these assumptions, whereas the LM test or the Breusch-Godrey test is very general and does not make many assumptions. The first diagnostic test that we study is the most restrictive of the tests, that is the Durbin-Watson test. It is very important to know the assumptions that the test makes, and hence we dedicate this slide to that. The first assumption is that xi is a non-stochastic, since whatever regression analysis that we have studied and will be studying makes this assumption, hence it is not really something that we should bother too much about. The next three assumptions that we make are with regard to the particular functional form of the error term. The first of these is that the error term follows a first order autoregressive scheme or an AR1 scheme, that is sigma t equal to rho of sigma t minus 1 plus nu t, wherein nu t is a random component and rho is the dependence of sigma t on sigma t minus 1. Note that sigma t cannot be dependent on any other period's error term except for that of t minus 1. The second assumption is that there is no lagged version of dependent variable among the explanatory variables. That is, if we are studying yt as a function of several variables, then one of these explanatory variables cannot be a lagged version of yt, such as yt minus 1 or yt minus 2. The third one is that there is an intercept term in the regression model. So as you see in this particular model, there has to be an intercept term alpha. So the steps of running the Durbin-Watson test is to first run the original regression. So a regression that we are considering is that yt is a linear function of x1t and x2t. Once we run this regression, we obtain the error terms or ETs. Using these ETs, we have to calculate the Durbin-Watson statistic or the Durbin-Watson D statistic. So we find out the difference of ET from ET minus 1 for all t starting from 2. We square this difference and then sum it over all t from t equal to 2 to t equal to n, and we divide it by the sum of ET squares from t equal to 1 to t equal to n. This gives us the Durbin-Watson D statistic. Alternative way to find out the D statistic is to first obtain an estimate for rho, that is the linear dependence of sigma t on sigma t minus 1. One way of finding rho is to multiply ET by ET minus 1 for t equal to 2 to t equal to n and summing this up and then dividing it by ET squares summed up from t equal to 1 to t equal to n. Another way of obtaining rho is to run the actual regression as Et equal to rho into Et minus 1 plus nu t. Remember that since we are taking Et as proxy for sigma t, hence the rho that we get in this case can be called rho hat, or a proxy for the actual rho. From an estimate of this rho, we can then obtain d, which is given by d is approximately equal to 2 into 1 minus rho. So what we obtain is a diagram such as this. Since d is approximately equal to 2 into 1 minus rho, then as rho equal to 0, that is as we see no autocorrelation between Et and Et minus 1, then d tends to 2. Hence, from a scale of 0 to 4, d equal to 2 represents a case of no autocorrelation. As rho tends to 1, that is as we see a perfectly positive autocorrelation, d tends to 0. Hence the left hand limit of this diagram, which is d equal to 0, refers to the case of perfect positive autocorrelation. As rho tends to minus 1, that is as there is perfect negative autocorrelation, d tends to 4. Hence on the right hand side of this diagram we see d equal to 4, that is perfect negative autocorrelation. Hence when we obtain an estimate of d, any d from 0 to 2 would make us believe that there might be positive autocorrelation, whereas any d from 2 to 4 might make us believe that there is some kind of negative autocorrelation. Now how we actually carry the formal test is as follows, that given the sample size n and the number of explanatory variables k which does not include the intercept, Durbin and Watson calculated du and dl. We will first find out what are these du and dl referring to. As we have calculated for all the tests such as a t-test or a normal test, we see that there is a critical limit beyond which we would say that the null hypothesis is rejected, and within which we would say that the null hypothesis is not rejected. Similarly, there is a value called d critical. So when we are considering only positive autocorrelation, then any d value which is to the left of d critical would make us reject the null that there is no autocorrelation, and any d value which is to the right of d critical, and rather between d critical and d equal to 2, would make us not reject the null of no autocorrelation. However, finding out these d critical values for different specifications of the model is informationally very challenging. Hence what Durbin and Watson did was to calculate an upper limit for d and a lower limit for d, which is du and dl respectively. So the actual d critical value lies somewhere between du and dl, and for those of us who have to depend on the tables as calculated by Durbin and Watson, there will always be an indecision region between dl and du. If we get a d value which is between dl and du, we cannot be sure whether it is above d critical or below d critical, and hence we are not in a position to either reject or to not reject the null hypothesis. However, if you obtain a d value which is lower than dl, that is which is to the left of the point dl as marked on the graph, then we can reject the null hypothesis, because we are sure that if the d value is less than dl, then it is surely less than d critical also. Similarly, if we obtain a value which is between du and d equal to 2, then we are not in a position to reject the null hypothesis, because given that d is greater than du, hence d will also be greater than d critical, and hence we cannot reject the null. In the less likely case of negative autocorrelation, the interval is given by 4 minus du and 4 minus dl. For obvious reasons, 4 minus du lies to the left of 4 minus dl. Even in this case, the d critical lies somewhere between 4 minus du and 4 minus dl, but its precise value is not known, and hence the region between 4 minus du and 4 minus dl is the indecision region. The region between d equal to 2 and 4 minus du is the region where we do not reject the null hypothesis because it is lower than d critical, and the region between 4 minus dl and d equal to 4 is the rejection region. However, since the Durbin-Watson d test has a lot of assumptions, we now turn to relaxing these assumptions. First, let us consider Durbin's H test. The other three assumptions of non-stochastic excise, AR1 and intercept are retained, but now we can handle the lagged version of dependent variables in the model. So for example, we can now handle a model such as yt equal to alpha plus beta 1 yt minus 1 plus dependence on other independent variables such as x2t or x3t. To calculate Durbin's H statistic, we first need to calculate the Durbin D statistic as we have previously done. Using the Durbin D statistic, we now modify it to create a new statistic called Durbin H statistic using this rather complicated formula, which is 1 minus d by 2 into root of n by 1 minus n into variance of beta 1. This H statistic follows a normal distribution with mean equal to 0 and variance equal to 1, which you would identify as the standard normal distribution. Hence we run a simple significance test with the null hypothesis that d equal to 2, that is h equal to 0. Hence the null hypothesis is that there is no autocorrelation, and if we are able to reject the null hypothesis given our value of h, then we can conclude that there is evidence of autocorrelation. The Durbin's H statistic also suffers from certain problems, and its limitations are given here. Firstly, it can only be used when 1 minus n into variance of beta 1 is less than 1. This is fairly obvious from the formula used to calculate the H statistic. The second limitation is that this is a large sample test, and hence even though some authors prefer to use n minus 1 instead of n to calculate the H statistic, it should not really make a difference. Thirdly, it can only handle AR1 schemes for the lagged version of the dependent variable, that is when yt is a function only of yt minus 1 and not of yt minus 2 or yt minus 3. Fourthly, it has been empirically seen that the Durbin H test is not a very powerful test. We now turn to a very general test which is known as the Breusch-Godrey test or the LM test. We can handle any kind of functional form for sigma t. That is, we can follow any ARP scheme such as sigma t can be a function of sigma t minus 1, sigma t minus 2 all the way up to sigma t minus p. What we have to do in order to calculate the Breusch-Godrey test is to run the original regression as follows, that is yt as a function of alpha plus beta 1 x1t plus beta 2 x2t plus sigma t. We then obtain the ETs and run the following auxiliary regression. We express the ETs as a function of all the independent variables considered in the original regression, that is x1t and x2t in this case, and also of all those error terms which determine this period's error term. So if we are considering ARP scheme, then we will take error terms up to previous periods. Once we run this auxiliary regression, there are two ways which we can go about to test the null hypothesis. The first alternative were given by Breusch and Godfrey themselves. They said that for the auxiliary regression we can calculate r square, and then for a large sample n prime into r square will follow a chi-square distribution with p degrees of freedom, wherein remember that p is the ARP scheme that we are following, where n prime equal to n minus p. Again, since this is a large sample test, hence the difference between n prime and n should not be statistically different, and hence some authors prefer to use n. The null hypothesis is that there is no autocorrelation, that is rho t minus 1 is equal to rho t minus 2 is equal to 0. Now given that it follows a chi-square distribution with p degrees of freedom, we can test whether n prime into r square is significantly different from 0 or not. Once we can establish that it is significantly different from 0, we can reject the null hypothesis, and hence we can conclude that there is evidence of autocorrelation. The second alternative is to run the original auxiliary regression that we have talked about previously, after which we can impose linear restrictions, that is rho t minus 1 is equal to rho t minus 2 is identically equal to 0. This kind of linear restriction will give us a restricted regression model, that is ET is equal to alpha naught plus alpha 1 x1t plus alpha 2 x2t plus epsilon t. Note that in this restricted linear regression model, we are assuming that the error term is not dependent on any of the previous period's error terms. Hence, after we have run this original auxiliary regression and the restricted regression model, then we can obtain the residual sum of squares or RSS and then test for the validity of the linear restrictions as we have previously done in other modules. The test statistic is a rather familiar one, in which in the numerator we have the difference between the residual sum of squares in the unrestricted and the restricted model, which we divide by the number of linear restrictions m, and then we divide this numerator by the denominator, which is given by the residual sum of squares in the unrestricted model divided by n minus 1, where n is the sample size and m is the number of linear restrictions. This follows an F distribution with m degrees of freedom in the numerator and n minus m degrees of freedom in the denominator. If we are able to get a significantly different value than 0, then we can reject the null that there is no autocorrelation and conclude that there is evidence of autocorrelation. We now turn to the remedies of autocorrelation. We consider two remedies. First is the first difference method. The second is a method of which it is a specific form, that is the generalized least squares method. So first let us talk about the more specific form, that is the first difference method. In the first difference method, what we are assuming is that rho equal to 1. Given our assumption that rho equal to 1, sigma t minus 1 becomes equal to nu t, which we have previously assumed is a normal distribution which does not show autocorrelation, and hence we have corrected for the problem of autocorrelation. To actually do this process, we first modify all dependent and independent variables as follows. We take a new variable which is yt star, and it is given by yt minus 1. This is why this is known as the first difference method, because we take the difference over one time period. Similarly, we do the same process for all independent variables also. We now run a modified regression equation, which is yt star is equal to alpha plus beta 1 x1 t star plus beta 2 x2 t star plus sigma t. When we expand and write it, we see that it is essentially running a regression between the first differences now instead of the actual variables. We thus obtain estimates of alpha, beta 1 and beta 2 which are free from autocorrelation. The problem with the first difference method is that it is valid only for AR1 schemes, and that it is valid only when correlation coefficient rho is not statistically different from 1. Remember that rho is not likely to be equal to 1 in many cases. However, the question remains whether this difference is statistically significant or not. Hence, in cases wherein we cannot really assume that rho equal to 1, we turn to the next method, which is the more generalized least squares method, or the GLS method. The steps required for the GLS method is to first obtain an estimate of correlation coefficient rho. Two of the methods are ones that we have previously dealt with. The first is to find out the product of ET into ET minus 1 for all t starting from 2 to t equal to n and summing them up, and then we divide this sum by the sum of ET squares when t equal to 1 till t equal to n. This is one of the methods of obtaining an estimate of rho. The second method that we had previously talked about was to run the regression ET equal to rho into ET minus 1 plus nu t. Now a third method that we can use is to first find out the Durbin-Watson d statistic and then use that statistic to find out rho using the formula that we had previously used for finding d. A relation between d and rho that we had previously talked about was d is approximately equal to 2 into 1 minus rho. Now moving around the terms, we can get that rho is approximately equal to 1 minus d by 2. So once we have an estimate of rho from either of these three methods, we can transform all dependent and independent variables as we have previously done for the first difference method. However, instead of subtracting yt minus 1 from yt, we now multiply yt minus 1 by rho and then subtract from yt. Similarly, we obtain new independent variables such as x1 t star equal to x1 t minus rho into x1 t minus 1 and x2 t star equal to x2 t minus rho x2 t minus 1 and so on. Now we run the modified regression equation such as yt star equal to alpha plus beta 1 x1 t star plus beta 2 x2 t star plus sigma t, like we have previously done for the first difference method. In this way, we obtain estimates of alpha, beta 1 and beta 2 which are free from autocorrelation. Even though the GLS method is very general, it does suffer from some problems. Firstly, the one that we have seen right now is valid only for AR1 schemes. However, the method can easily be adapted for ARP schemes by modifying the dependent and independent variables as follows. So instead of just subtracting rho into yt minus 1 from yt to get yt star, we can now subtract the entire ARP scheme as we suspected. So we obtain estimates of rho t minus 1, rho t minus 2 and rho t minus p, and then subtract it from yt star. However, note that finding these estimates of the various rows will be quite difficult. The second problem that we encounter is because we take differences, we lose one observation. Hence, the sample size reduces by 1. This might be a major problem for smaller samples. Hence, there is a method for actually getting back one of the samples, and this is known as the Prey-Winston method. How we generate the first sample in this case is to take y naught star, which is equal to y1 into root of 1 minus rho square. Similarly, x naught star equal to x1 into root of 1 minus rho square. We can now add this y naught star, x naught star, x1 star and so on to our modified variables which we had previously obtained, and then run the modified regression with the larger sample. In this case, we have taken care of the autocorrelation problem because the new sigma t does not suffer from the same autocorrelation that we had previously talked about. This brings to an end our discussion of the autocorrelation problem.